Hello, welcome to the probability class. Today we will solve a few problems on the topic of conditional probability and Bayes formula. Let me bring out the PPT. Here it is. First problem. One card is randomly drawn from a pack of 52 cards. Consider the events. We are considering two events. The event A says that the drawn card is a spade, and event B says that the drawn card is an ace. We will have to show that these two events are independent. Let me take the pen first. Yeah, I have taken it. So these are the two events, event A and event B. Altogether, there are 52 cards, and we are picking up one randomly. We can pick up any of the 52 cards. So sample space size is 52. Number of favorable events for the event, number of favorable outcomes for the event A is 13 because there are 13 spades. That means probability of A equal to 13 by 52 equal to 1 by 4. Size of B is what? The drawn card is an ace, and there are 4 aces. That means probability of B equal to 1 upon 13. What is the event AB? That means the drawn card is a spade as well as an ace. In other words, the drawn card is the ace of spade. There is exactly one choice. That's why this is 1. That means probability of AB equal to 1 upon 52. After this calculation, we can see that PA into PB is also equal to 1 upon 52. That's why PAB equal to PA into PB. In other words, the condition for independence is satisfied. Hence, A and B are independent. So we have solved this problem. Next problem talks about rolling 10 fair dice together simultaneously. And two events are given. We'll have to find out the conditional probability of one based on the other. What are the two events? Event B, at least 1, 6. In other words, out of those 10 dice rolled, at least one appears to be a 6. And event A is 2 or more 6s. And we need to compute probability of A given B. As such, these events look a little complicated. Let's write down two more events. number of sixes out of 10 rolls of fair dice, or roll of 10 fair dice can be either 0 or 1 or 2 up to 10. How about these two events? Event C, there is no 6 at all. That means event C is this thing, that when you roll the 10 dice, none of them appears to be a 6. And event D, exactly 1, 6. For this thing, in order to compute this, the formula requires us to compute two things: probability of A intersection B and probability of B. What is the event B? No. Event B we know. Observe this thing. A is a subset of B. Right. Why is it so? Because when event A occurs, that means 2 or more 6s have appeared. And in that case, of course, event B is also satisfied, because at least one of them is 6. That is also true. That's why A is contained in B. That means AB is same as A. So that means probability of AB is equal to probability of A. That's why it's enough to calculate probability of B and probability of A. Because why? This is probability of AB by probability of B, and we have already seen probability of AB is nothing but probability of A. So this ratio, we need to compute these two numbers, numerator as well as the denominator. And that's why we are bringing, for the ease of computation, we are bringing these two other events. We will see how it will ease our calculation. Let us call P0 probability of C and P1 exactly 1/6 is equal to probability of event D. Look, B complement is which event? B means at least 1/6. So its complement is no 6 occurs. That means event C. So probability of B is equal to 1 minus probability of B complement. We know that thing from basic rules of probability or basic properties of probability, and that's why this is same as 1 minus probability of C. That is probability of C, we have denoted that thing by P0. So 1 minus P0. And what is A complement? A complement means, A means what? A means 2 or more 6s. So its complement means either there is no 6 or there is exactly 1/6. That means this is equal to C union D. C will take care of that thing that there is no 6 at all, and D will take care of that part that is exactly 1/6. That's why A complement is nothing but C union D. And C and D, these two events are mutually exclusive. That's quite clear. So probability of A complement is nothing but PC plus PD, and that is same as P0 plus P1. That means probability of A is equal to 1 minus PA complement is equal to 1 minus P0 minus P1. So we have got PB and PA in terms of P0 and P1. Putting those things here, what will we get? That will be, I'm just rewriting this thing. This part is PA is equal to 1 minus P0 minus P1 by 1 minus P0. That means 1 minus this 1 minus P0 divided by 1 minus P0 is 1. So I'm left with P1 by 1 minus P0. Let me erase some part of this so that I get more space. So P of A given B is equal to 1 minus P1 by 1 minus P0. We need to compute this thing. Now, what is P0? That is probability of C. And C is which event? C means there is no 6 at all. These are the dice. There are 10 dice altogether. Dice number 1, 2 up to 10. So for event C, C is what? C is no 6 occurs. So C means no 6. So for 6, let's count the number of favorable situations or favorable outcomes. As there can be no 6, for position number 1, that is for outcome of die 1, we have 5 possibilities. And for 2 also we have got 5 possibilities. And similarly for 10 also 5 possibilities. So altogether, how many possibilities we have? We have total number of favorable cases for C is equal to 5 to the power 10. And what's the sample space size? Omega. There is no restriction whatsoever on any of the outcomes. So each position can be filled in 6 many ways. That's why size of omega is equal to 6 to the power 10. So we get probability of C is equal to 5 to the power 10 by 6 to the power 10. Now let's come to the event D. Event D means exactly 1, 6. Now that 6 may appear in any of these 10 places. So let's first choose the position. Choice of position can be done in choice of position where 6 will appear. Choice of position for 6, for the 6, that can be done in how many ways? 10C1, that is 10 ways. Once that choice is made, suppose 6 appears here. So this position is fixed. Now the remaining positions, we'll have to see how many ways we can fill those. For position number 1, now there are 5 possibilities because 6 cannot appear anymore here. 5 possibilities. And position number 3 also 5 possibilities, and so on up to position number 10. So once this choice is made, remaining positions can be filled in how many ways? 5 to the power 9 ways. So combining these two, this one and this one, how many total ways are there? 10 multiplied by 5 to the power 9. And we know already the sample space size is 6 to the power 10. So probability of D is equal to 10 into 5 to the power 9 by 6 to the power 10. Remember this. Now let's write down both and get the answer. So let me write down the same, this P1 here so that we can use that thing later. 10 into 5 to the power 9 by 6 to the power 10. Let me erase this part now. That should be enough. So using this formula, we get one minus, what is P1? 10 into 5 to the power 9 by 6 to the power 10 divided by 1 minus 5 to the power 10 by 6 to the power 10. Now here, in this part, let's multiply both numerator and denominator by 6 to the power 10. That way, we will get 10 times 5 to the power 9 divided by. This is the final answer. So the lesson of this exercise is sometimes the complicated event can be for a complicated event or a complicated looking event, you can compute the probability by considering some other events and expressing your event of interest in terms of those, as we did here. Here, the question is in terms of A and B. However, for the ease of calculation, we brought in two new events, namely C and D. Let me clear this and let's go to the next slide. If two events A and B are independent, then show that A and B complement are also independent. And the fourth question is about drawing two cards. First, let's address problem number 3. So it's given that event A and B are independent. Sometimes we write in short, in depth, to mean the same thing, independent. Algebraically, what does it mean? That means P of AB that means I can subtract both sides from probability of A. If I do that, I get right hand side is nothing but PA. I can take common 1 minus PB, right? Let's see what is the left hand side. This is our omega. Here is A and here is B. So this is A, this is B, and this is AB. This part is AB. And what is this part? This dotted part? That's A and B complement. Because in this part, in the dotted part, A occurs, but B does not occur. So combining these two things, I can write AB equal, A equal to AB union AB complement. And see, AB and AB complement, that is this one and this one, these are two disjoint events. And what do you know about disjoint events? When you do probability of the union, it decomposes as summation of the individual parts, like volume or area of non-overlapping regions. So I can write it, once I get this thing, I can use that thing to write PA is equal to P of AB plus P of AB complement. So using this thing, I can write this is probability of AB complement is equal to 1 minus, not this. This gives probability of AB complement is equal to PA minus P of AB. I get this. And using that, I can write the left-hand side of this thing, this equality, as probability of AB complement. Once I do that, what does this mean? Probability of AB complement is equal to PA, and this part I can replace with probability of B complement. That's why we get this, and this equality implies A and B complement are independent. That's what we had to prove. Look, this is not surprising. This is not surprising, because if two events A and B are independent, A and B are two events which are independent. And look, B and B complement, information wise, they are identical. Why I am saying so? Because if I am told that B has occurred, I know that B complement has not occurred, and vice versa. In other words, if given information about B is equivalent in a sense with information given about B complement, in that sense. So if A and B are independent, you expect A and B complement also to be independent. But that is just expectation, and we showed algebraically that that actually is true. And what's the lesson of this? Once you understand the lesson of this, then we can see some other things. A and B are two events which are given to be independent. Then, by virtue of this exercise, I can take complement of one and still that will be independent with the others. Independent with the other. Then implies A and B complement. In essence, what it is, I can take complement of one event and still it will be independent with the other. Are independent. And that will give me also A complement, because now I'm complementing this thing by virtue of the same understanding. A complement and B complement are independent. And again, taking complement of this one, I can write and B are independent. So I don't need to do algebraic proof again repeatedly for each one of them. But once I make this observation, then all these things follow immediately. That if A and B are independent, then so are any combination. A, B complement, A complement B, A complement, B complement, any combinations, any combination, either this or this or this, these combinations will be independent also. This is an interesting problem. Let's talk about this. There is a well-shuffled deck of 52 cards. And we are picking up 2 cards in succession. That's important, in succession. That means 1 by 1. So here is the first card, and here is the second card. And it's being done randomly. So what's the sample space size? You know, that is 52 into 51, because first card can be drawn in 52 ways, and second one, after the first one is done, second one can be done in 51 ways. So 52 into 51. That's the sample space size. Here we are given some information, and we are supposed to compute conditional probabilities of these two things. Of these two things. What are we given? We are given the first drawn card is spade. What is the probability of that event? Look, for the first drawn card, in order to B talks about only the first drawn card. So in order to compute the probability of B, we don't need to consider what happened for the first drawn card. That's one way to look into it. Other way is actually count all the possibilities. So if you just do it that way without looking into the details of what is actually occurring in the second card, then how much is the how much should be the probability of B in that case, just considering the first card? So that should be equal to 13 by 52. And let's see in terms of the whole experiment if that thing is true. For the first card, we are considering the event B. For the first card, we have got 13 choices. We are trying to compute, we are trying to find the favorable outcomes for B. So for the first card, we have got 13 possibilities, any of the spade cards. And once that is done, the remaining card, that is the card number 2, can be anything, that is any of the 51 cards. That's why size of B or the number of favorable outcomes for B is equal to this. And we know already size of omega is this thing. So probability of B becomes ratio of these two things, 13 into 51 by 52 into 51, that is 13 by 52. You can write this thing as 1/4. So probability of B we have already found out. And you know that while computing conditional probability, this will come as the denominator. So the denominator part is taken care of. Now let's talk about these two events. The second one is also a spate. Let's identify the events. And event D, the second one is an S. Now for C, how many favorable outcomes are there? The first card should be, excuse me for a moment. Yeah, we need to compute what? Probability of C given B. That means probability of CB by probability of B. We have already found out probability of B. So we need to compute probability of C intersection B. C intersection B is which event? This event says, because of B, it says that the first card should be a spade, and because of C, it says that the second card should also be a spade. Let's see how many ways it can be done. The first card can be any of the 13 spade cards. And once that choice is made, the second one can be any one of the remaining 12 spade cards. That's why size of CB is equal to this much. So we get this implies probability of CB is equal to 13 into 12 by 52 into 51. Right? Now from this one, we get, I can write this thing as, I'm just writing here to get more space. Because probability of B is 13 by 52. Look here. And probability of CB is this much. Now 13 by 52 factor is common in numerator as well as denominator. So this becomes 12 by 51. So you have got probability of C given B. In other words, this conditional probability you have got to be 12 by 51. This one is 12 by 51. What about this one? Again, we are drawing two cards as before, first and second. So the event D is, the second one is an S. So we need to find out DB. What does DB mean? This event means the first drawn card is S. So you have got S here. I'm sorry, that's not the case. The first drawn card must be sped because of B, and the second drawn card must be S because of what? Because of D. Let's examine how many ways that thing can happen. Now, spade has got these cards. I drew it in the wrong place. Two, three, up to 10, then Jack, Queen, King, and Ace. These are the possibilities. Now, altogether, how many aces are there? There are 4 aces, one from each suit. Now, for the first position, if the card is drawn from anything from 2 to K other than S, then the first one, let me write it down in 2 separate cases. That's one possibility. The first card may be non-S spade. In that case, how many possibilities are there for the first position? There are 12 possibilities. And once that is done, for the second position, that is for the second card, how many choices do we have? We have got each of the 4 aces is available. So we can fill the second position in 4 ways. That's why under this, we have got these many possibilities. Let me repeat. The first card drawn can be drawn in 12 ways. Other than the ace of spade, we can pick up anything because we are under this case. And once that is made, once that choice is made, for the second position or second card, we have got 4 possibilities. That's why 12 into 4 possibilities under this. Now, what happens if the first drawn card is ace of spade? In that case, there is no more choice for the first position because the first position is fixed with ace of spade. How many ways can we fill the second position? Only 3 ways, because that this ace can come from either club or diamond or heart. So there are 3 possibilities. So altogether there are 3 possibilities here. That's why putting them together, total number of possibilities should be summation of these 2, that is addition of these 2. Total 48 because of 12 into 4 plus 3 equal to 51 possibilities. So DB, size of DB is equal to 51. That means probability of 1 by 52. Right? So probability of DB is 1 upon 52. And we already know probability of B is equal to 1 upon 4. So probability of D given B is the ratio of these two numbers, 1 by 52 by 1 upon 4. So 1 upon 30, 1 upon 13. Right? This is 1 upon 13. Okay. I want you to observe some interesting thing here without getting into any further calculation, because we have already done lots of calculation here. Intuitively, how much should be probability of D? D is asking about only the second card. And the question is, what is the probability that the second card will be an S? Right? So, in a sense, that each card will have same chance of occurrence as the second card. Out of the deck of 52 cards, each card should have same chance of occurrence as the second card by symmetry, because we are doing the whole exercise randomly. So looking at the thing that way, intuitively you can say that probability of D should be 4 upon 52, because there are 52 possibilities and only 4 are favorable. So probability of D should be equal to 4 upon 52, that is 1 upon 32. It should be. Intuitively, it is quite clear. Although we can write the whole thing again systematically using mathematics, using both the cards and both the positions, but intuitively it is quite clear that it should be true. Excuse my extremely bad handwriting here. So once you find this thing, you can combine these two things together and see probability of D given B is same as probability of D. In other words, even D is independent of D. So B and D are independent. That's a nice thing. So this observation comes out. Okay. Now, these two problems are taken care of. Right? These two are taken care of. Now, I want you to observe something out of this exercise that will be helpful for solving other problems. Let me bring it out systematically. This experiment has got two components or two parts. First part is drawing the first card and then drawing the second card out of that 52 card deck. So these are the two components. Now we are given something about the first component, and the question is about the second component of the random experiment. Now, in order to answer, so these are the two parts, part 1 and part 2. These are the parts of the random experiment. Part 1 is this part and part 2 is the second part. After part 1, one card is removed from the deck. So we have some configuration of cards here, some collection of cards here. One is missing. And you will agree that in order to answer any of these two questions, it's enough to know if somebody tells us what is the exact configuration here. So what do I mean by configuration? That will depend on the question. So for the first question, it's enough to know after part 1, what is the configuration? This way, that how many spades, or let me do this thing. How many, I'm just enlarging this thing. This is the configuration left after part 1. How many total number of spades remaining, and total number of cards. If we know these two things, by the way, total number of cards is anyway known because 1 is missing, so that is 51. That's known. And somehow, if we know after this exercise how many are remaining here, total number of spades, then it's enough to answer this question, because we only need to know this configuration after part 1. And then part 2 will be exercised on this thing, because part 2 will be exercised on this, right? So it's enough to know this configuration after part 1. So if look, some information is given. What is the information? That the drawn card is spade, but not the exact card. We are not told exactly which card is drawn. However, if somehow we know this configuration, then you will agree that we can immediately calculate the conditional probability. That is, what is the probability that the second card will also be a spade? And for this one, what is the configuration? For this one, configuration will be, please understand, the configuration that you will be interested in order to solve the problem will depend on the question. For the second one, the question is asking about S. So here, your configuration of interest will be number of S's remaining and total number of cards. This is equal to 51. That is obvious. And number of S's, if somebody tells us, then we can immediately tell that after part 2, this will be the answer. So the configurations will depend on the question, the configuration of interest. Now here, look at the first question. The first question asks you that what is the total the probability that the second one is a spade, and in this case the configuration is this thing. What is given? It's given that the first drawn card is spade. That's given to us, right? First card is spade, that is given to us. Once that is given, we are trying to find out after part 1. After part 1, which configuration it leads to. After part 1, right? Now, about part 1, we don't know the exact outcome, but we know that the outcome is a spade. So no matter which spade card is picked up, there are altogether 13 spade cards, starting from 2 to 10, then Jack, Queen, King, and S. no matter which one is picked up, we are left with the same configuration. The number of spades will be equal to 12. Now we can write down this number, and total number of cards is 51. That means for no matter what is the, I'm just repeating the same thing to emphasize, no matter what is the choice made, because we are given that the first drawn card is a spade, we are left with this configuration that there are 12 cards of spade and total number of cards 51. So after part 2, the answer for question A must be equal to 12 by 51. So that is because this configuration, I'm emphasizing the term configuration, because this configuration does not depend on the exact choice made in part 1, the final answer will also be equal to same 12 by 51. And we have already seen that while we computed it mathematically. That's an interesting observation, which it all depends on what kind of configuration it leads to. And if the configuration that it leads to is immaterial of the choice made in part 1, because you are given some information about part 1, that's what is given to you. And based on that information given, if you can conclude that your configuration of interest, the configuration of interest is this one, is same, then you can immediately calculate the probability. Instead of getting into that long calculation we did, we first found out what was the total number of favorable cases for C intersection B, and then find out probability of that and take ratio with probability B, all those things. Here, intuitively, you can argue that this should be the answer and it should be correct. But all the thing I'm repeating again, it depends on the fact that no matter which card is chosen under this condition, under which condition? Under this, under the given condition, we are left with the same configuration of interest. Here the configuration of interest is this one. That's why we can conclude that the answer is this. Now, come back to this one, this question. Is the same thing true? The answer is no. Because if the first drawn card is ace of spade, then how many aces are we left with? Ace of spade is already gone, so we are left with 3 aces. And then in that case, the answer will be 3 by 51. However, if the choice of the spade card is anything other than ace, then that ace of spade is also remaining. So in that case, we'll be left with 4 choices of ace. So the answer will be in that case 4 by 51. Now, which one to choose? No, you are getting 2 different answers. And actually, you cannot do exactly this way. You need more fine tuning. And we are leaving that part here. But this observation is important because often you will see situations like this and your calculation can be a lot easier if you keep this thing in mind. That here you can actually make use of this argument of similar leading to similar configuration. Keep that thing in mind. That's very useful. Question number 5. In a bridge game, West has got no ace. What probability should he attribute to the event that his partner having exactly 1 ace? So West has got no ace and he is just trying to find out the probability that his partner, who is West's partner, that is East, West, that's East. East is West's partner. What is the probability that East also, no, sorry, East has got exactly 1 ace. We need to conclude that thing. Okay. Now, while playing card, the cards are distributed one after another. but all the things are being done randomly. So probabilistically, or answering questions about probability, you can as well do the distribution this way. That is, pick up any 13 random cards, give it to West, then pick up another 13 cards, give it to East, then another 13 cards, give it to North, and then give it to South. Into these four, you can see the experiment as one with these four components. Drawing 13 cards simultaneously and giving it to one person, then another 13 cards to another person, and that way. If you visualize the thing this way, your computation will be easier. But equivalently, distribution-wise, probabilistically, it is the same thing. Whether you give the card one by one or pick up 13 and give it to one person, and so on. So here are the players: North, East, South, and West. West has got no S. And while playing bridge, of course, West cannot see East's hand, but West is trying to compute or trying to find out what should be the probability that East has got exactly one S. That's the probability he or she is trying to compute. Look, here we can make use of the last discussion. You can see this thing as multi-component random experiment. Part 1, part 2, 2, 3, and 4. 4 components. Now, we are not interested in North and South, so we can just think that the first part is giving 13 cards to West, and then giving 13 cards to East, and then of course part 3 and part 4. But for the purpose of solving this exercise, we can only concentrate on part 1 and part 2. That way it will look similar to the last discussion. And part 3, part 4, of course, what happens is none of our interest, because we already have got the answer. So part 1 is give 13 cards to West. That's part 1. And part 2, then give 13 to East. These are the 2 parts. Now, for part 2, and we are interested in knowing what is the probability of this thing after part 2 is performed. After part 2 is performed, right? And for that, what's important to us? What is the configuration of interest here? Configuration of interest here is number of S's remaining and total number of cards after part 1. And then part 2. Part 1, see, some information is given to you. We are already told that West has got no S. In other words, part 1 has not drawn any S card. So how many S's are remaining? S's are 4. And what is the total number of cards? 13 are already gone out of 52. So 39 are left. Right? So this is our configuration of interest. And no matter which exact choices are made, those 13 cards, we are invariably left with this configuration. And this is what is of interest to us. How many S's are there? And what is the total number of cards remaining. Look, here we cannot simply take ratio of 4/39 because here the question is a lot more complicated. But this is the configuration that is of interest to us, that you should be convinced about. Right? After part 1, we are left with this configuration. So it's enough to look into this configuration and answer the question. So if we do that, if we restrict ourselves to this configuration and try to answer the question, we are drawing how many cards here? 13 cards. So restricted to this part, what's the sample space size here? Drawing 13 cards out of 39 total cards. So 39C 13. And our event A is what? Event A is East gets exactly 1S. That is event A. Exactly 1S. This is the event A. So the conditional probability of A, for conditional probability of A, we need to also count the total number of favorable cases under this scenario. So let's get into that. What is the total number of favorable scenarios? How many aces East should get from this configuration? Should get exactly 1 ace. So how many possibilities are there about the aces? See, we are giving 13 cards to A. 13 cards to East. This is East. Now, from the aces, exactly 1 ace should come here and 12 non-ace. How many ways can we give 1 ace out of these 4? Ace can be given in 4C1 ways. And how many ways can we give the 12 non-ace cards? How many non-ace cards are there? That's important. See, in order to answer this, it's not straightforward. So we need to find out something else, something more also. What is that? What is the total number of non-ace cards in this configuration? Total 39, aces 4, so non-ace cards are 35. Non-ace cards are 35, so 35C 12 ways. So 12 non-ace cards can be given in 32C 12 ways. That's why East can be given the cards in 35C 12 these many ways. Now we have found out both the things. So what should be the conditional probability? Conditional probability of A, given that whatever that that event, I'm not writing it down, given that information, you should actually identify that event also. Event B is equal to so and so, and probability of A given B will be same as 4 times 35C12 divided by 39C13. Total number of possibilities is 39C13, and these are the number of favorable scenarios. So 4 multiplied by this divided by this thing. See how easy it became after elaborating on that observation. Probability subject is quite intuitive. So making this kind of observations actually helps you a lot in both understanding the situation far better and also solving problems. Here is the next problem. There is a city. We are assuming that there are equal number of men and women. It's a huge population. And there is a proportion of colorblind people among men and women. Those ratios are given to you in some empirical figures, which are 5 men out of 100 and 25 women out of 10,000 are given to be colorblind. And we are selecting one person randomly from the city. It's given that the selected person is colorblind, and we are doing back calculation. What should be the probability that the chosen man is, the selected person is a man? So the selected person is given to be colorblind. What is the probability that the selected person is a man? That's the question. So let's identify the events. B is the selected is colorblind. C, the selected person is man. No, don't use C. That way, let's write it as M, and W, the selected person is a woman. Okay. And we are supposed to compute probability of M given B. We will apply Bayes formula here. That helps us revert the conditioning. That's the basic gist of Bayes formula. And that way it becomes B given M multiplied by probability of M divided by probability of Now, what are these things? Among the men, we know that 5 out of 100 are given to be colorblind. So probability of is 5 by 100, that is 1 upon 20. 1 by 20. Probability of colorblind among women, that is equal to 25 out of 10,000. 1 by 400. Probability of M equal to probability of W is equal to half, because there are roughly same number of men and women. So we have got these things. Now putting all these things here will give us now both numerator and denominator we can multiply by 40. That way we will get 1 upon 1 plus 1 by 20. That is 20 by 21. So given that the selected person is colorblind, the chance of the person being a man is lot more compared to what it should be, that the probability that it should be it is a woman. Sorry, let me repeat that given the information that the selected person is colorblind, the chance of the selected person being a man is lot higher than the chance of the selected person being a woman. What's the chance of the selected person being a woman? That is 1 minus 20 by 21, that is 1 by 21. So the chances are in the ratio or in odds of 1:20. Nice. That brings us to the end of this session. Let's close these things. All right. Hope you understood these things. these exercises gave us some ideas in more clarity about how the problems in condition and probability should be handled, and some insights also, like about 2 parts of the random experiment, part 1 and part 2. If we have some information about part 1, how we can ease our calculation sometimes if the given information leads to the same kind of configuration, etc. That's quite helpful intuitively. And try to solve more problems. That way your ideas get a lot clearer. Hope you enjoyed it. Thanks for listening.